side, we have Noah Petro from Goddard Space Flight Center to talk about what the moon looks like and the moon's topography. So, thanks, Noah.
All right. Yeah, thanks, Angela. And I have a set of slides that I've prepared, and I will try to go through those as briskly as possible. If you've joined us over the last 2 days, most of this will be review. You heard some amazing presentations from the Lola and LROC teams all the last 2 days. So some of it's review, but I'm then going to go a little bit off of prepared remarks, because I think one of the issues that we've addressed here is, just the simple question: how do I find the data? How do I get access to it? And so I want to spend a little bit of time walking through that in real time. Always a little dangerous. Hopefully I'll save some time for questions, but I've appreciated over the last few days the disconnect that I have with members of this workshop in trying to find the data and the knowledge of what we have. So I'm going to walk through a little bit of kind of what we have from LRO. Again, some of us will be review, but then I want to get into working with the data. Dan Moriarty, who works with me at Goddard, is on as well. He and I work with this lunar data, and so he's also here as a data user as well, so potentially can answer questions that may come from that side. Just emphasize again, and I do want to sound like a broken record here, LRO is a healthy operating spacecraft with a healthy and operating science teams. We have the people who are making the data, calibrating the data, working with the data, improving the data, engaged with the mission right now. So now is the time to dig into these data sets, to raise your questions, concerns, but also ask for certain things. LRO serves the planetary science community. We serve NASA, but we're also in a position to serve new data products, generate new data products if we have the data that you need to make those products. So now is the time to do that. Don't wait months, years. Do it now. And again, feel free to ask me questions. And we want to get the data into the right hands as quickly as possible. So I'm going to jump into my prepared presentation here, but hopefully I'll have a little bit of time before my half hour is up to answer or get into a little bit of how to use the data. So let's see, provided that I'm not doing anything silly with my VPN, I'll be able to do this. Okay, so you should see my PowerPoint slides. And again, there's my email address. I'm the only Noah Petro at NASA. And so please feel free to contact me. I've already had a few emails come through asking questions. And so one of the bottom line answers, the short story is, we have the most robust, the highest fidelity topographic model of any object in the solar system at the moon, better than the Earth. The one thing we can say that the moon is better than Mars, that is that we got better topography for the moon than we have for Mars. I want to talk a little bit about what we have. You've heard about the instruments, and then I'll get at how do we find those data products. Let me start from the beginning with LRO. Again, LRO's reason for going to the moon was generating this type of data product. The data to facilitate landing and exploration at the moon, starting from the foundation of the topographic grid for the moon, the geodetic grid, upon which every other data product that we generate is laid. And so, this workshop, even though maybe 10 years ago, 11 years ago, we wouldn't have known this would have happened, this is the reason why LRO was sent to the moon, is to generate the material that you all need to facilitate landing and exploration at the lunar surface, not just in the topography, but the identification of hazards, whether it's craters, boulders, and of course, the amazing LROC narrow angle camera images that we have that facilitates doing those investigations. So again, we're here to support you. We've heard from Lola in previous days, and again, Lola is this 5-beam laser altimeter. With those 5 beams that go to the surface of the moon, we get these very precise measurements of topographic variation. We have global coverage from Lola when merged with the Kaguya datasets at the 60 meter per pixel spatial range across the entire moon. Closer to the poles, we can increase the density of coverage to get 5 meters per pixel coverage. These LOLA products provide us, again, this foundation upon which all of the other data sets are embedded. We have topography from the stereo images from the wide angle camera, and then at smaller scales, the narrow angle camera provides us 2 to 5 meter per pixel scales in targeted coverage areas. These targeted small scale topographic products really become the meat and potatoes of understanding topographic variation for equatorial regions that many missions hopefully will be utilizing in their exploration of the moon. We've talked about the topographic products, and again, one of the things that I want to keep emphasizing is that we can also get information from one or more images. You heard about the stereo photoclinometry as well as the AIM stereo pipeline work. We can image a site multiple times, and indeed for the areas near the poles, because of the density of coverage, we have dozens of images of any one particular location under varying illumination conditions. There's an incredible amount of detail that's recorded in those informations. While it may not be initially a topographic product, we can infer, again, hazards, boulders, craters from those multiple images. I highlighted on day one of this workshop, and I want to remind everyone of this underutilized data set from Apollo's 11, 12, and 14, these Apollo lunar stereo close-up camera images that capture at the micron to centimeter scale the variations in the regolith. This may not necessarily immediately jump to you as something that's a useful data set, but embedded in this is knowledge about the properties of the regolith at this scale. We go from the global, the local, to the hyper small scale, and each of these scales is an understanding of how the lunar surface behaves. This serves as a reminder that we know an awful lot about the lunar surface. There may be things that you want to know and may not be initially a data set that jumps to mind as saying, oh, well, we can understand the properties of the moon at the 60 centimeter scale. But between what we see here and the NAC and the LOLA scales, we know a lot and can infer to those intermediate scales. So LOLA data has over 7 billion topographic observations of the lunar surface. And again, with the density of coverage over the South Pole, really becomes this robust data set. With altimetry, we can get slope, azimuth, roughness, information about any particular location on the moon. This has been an incredibly useful tool for understanding the shape of the moon, of course, and giving us knowledge about areas of permanent shadow or near permanent illumination. And again, for portions of the poles, particularly poleward of 87.5 degrees, we have a 5 meter per pixel topographic data product. As Mike and Erwin have talked about over the last few days, we are in the process of coming up with special data products at the 5 meter per pixel scales for areas of the South Pole. We're doing that as a sort of a best effort for areas of interest, but certainly the moment that any particular landing site becomes, any particular position on the moon becomes an area for landing, that rises to the top of our interest in supporting those missions. Again, so there are products in the PDS that the LOLA team have generated that specifically look at roughness at the 100 meter scale. And so that's again at the scale of multiple LOLA measurements. We can use that understanding of roughness at that scale, and particularly in connection to places that we have explored, for instance, the Apollo landing sites, to infer what we might expect in terms of roughness at other locations. And again, this becomes one of the real skills of our team, is taking knowledge for particular locations and applying it to areas that we want to go, so that even if we don't have this experience on the surface, we can infer a lot about what to expect when we get there, especially when coupled with those high resolution images from the narrow angle camera. So going from the global scale to a more local scale, what we show here is an example of a large region, the Apollo 17 landing site and its environment, as measured by the narrow angle camera stereo observations. We can get these observations through slewing of the spacecraft, small slews. There are seasons of the year when we are under ideal illumination conditions. Again, getting these types of observations at the poles is challenging. We have been able to do that, but for particular areas of the poles, we already do have some of those 2 meter per pixel DEMs in hand. We can capture hundreds of images over the course of the year, but again, I've shown you maps of the type of coverage that we have from these stereo observations. We've imaged about 3% or so of the moon under these illumination conditions. So that's to say is that you may think that, oh, well, I have a particular landing site, a particular area of interest. I'm sure that they've captured it. Well, don't be sure of that, and definitely want to check with us to make sure that that data has been captured. This is an example at the right, bottom right of a fly-in using the narrow angle camera images and topography, just to highlight again what we can get out of these 2 meter per pixel maps. And it becomes pretty stunning when you get close to the surface to see the actual relief of the moon. Again, you can essentially go there virtually with our data sets. As a reminder, and one of the things that I always have to be reminded of is that the fidelity of this product is such that we can actually see the descent stage of the lunar module in our topographic and these 2 meter per pixel topographic products. So that to me is an incredible validation of the ability of these tools to suss out and measure small scale features on the moon. One of the important tools that I just remind everyone that we have is, there are a number of analysis products that have been developed by the terrestrial remote sensing community and terrestrial LiDAR community for understanding properties of the surface. And one particular one that's been valuable is understanding the ruggedness of the surface, how topography changes on small scales. TRI is one that's been used in analysis for multiple landing site studies. I'm going to highlight some of those here. This is from a presentation Brad Jolliffe gave several years ago in support of a Farside sample return mission study. And again, going from the image data to topography to now derived products, again, slopes at the 2 meter per pixel scale, and then this terrain ruggedness map, again, highlighting topographic variation on the meter scale. This is the type of analysis that we as the planetary science, the lunar science community have done for supporting our missions. Again, each individual mission that's going to the moon is going to have different requirements, different needs. The sooner that we understand those requirements and needs, potentially the better for getting those correct products into your hands. This is a map, and I apologize if it's a little challenging to see. The red outlines are of those available DEMs that have been processed by the LROC team. Again, it may look like, oh, well, we've got pretty good coverage, but that's probably, again, 98% of the moon doesn't have topographic models that have been produced for it by the LROC team at this scale. So again, don't assume that it exists just because you've shown interest in it. Please check with us. These are the 3 NAC LROC team produced DEMs for areas near the South Pole, one at the rim of Shackleton Crater, one along the connecting ridge between Dagger-Lash and Shackleton, and one at the summit of Malapert Massif. These become very valuable for, again, comparing what we know about places we've been to areas near the South Pole. This is just a zoom in on one particular product. This is the DTM that was produced for the Malapert Massif. Again, this was done several years ago when the European Space Agency, through NASA headquarters, communicated interest in these potential landing sites, and so the LROC team turned around these products. The link to that particular this particular product is provided at the bottom of the screen here. Let me talk a little bit about the 5 meter per pixel DEMs that the LOLA team has produced. You've heard about them in prior days. This is a new approach that the LOLA team has taken at creating these really hyper is not the right word, these cleaned up products. Requires human interaction. This is not an automated process to remove some of the artifacts that are embedded in the LOLA data. But these products are incredible resources, not just for understanding the topography of the moon, but in generating derived products. At the left, this is an example Dan Moriarty created, is a map of topography for one of these 5 meter per pixel DEMs. At center is a measure of slope. And again, you see the variability in slope. The green indicates areas that are between 0 and 5 degree slope. And then at right is a map of Earth visibility fraction. So again, this becomes some of these multiple derived products that can come from these tools. Again, polar landing site, we're interested in where the sun is going to be, but also where the Earth is going to be for communication reasons. And so this serves as a reminder that these high resolution data sets not only tell you about the topography, but derived products can shine light is partially a pun that I want to use to describe what you can do with these things, shine light on what we understand about what's available at the polar regions, or again, at lower resolution for other areas, more equatorial from the local data set. Okay, and so I have about 12 minutes left here. I have a number of links that are going to be in these slides. I'm going to put them up so that when this video is replayed, you can potentially go and find them. But I'm going to, for a moment here, go to a web browser and just highlight some of the ways to track down and use some of the data sets that we have. Before I do that, though, I'm going to do the dangerous thing of maybe taking a moment, Angela, to see what questions are in the chat window. Let's see. So Daniel, I'll respond to your question in the chat window afterwards. How are the hazardous roughness and slopes calculated? So there are multiple ways that the TRI, the Terrain Ruggedness Index that I showed, basically is using variation in topography around central pixels at various scales, going around to get a measure of how much topography is changing at that pixel scales. Are there data sets for solar radiation on the moon's surface? Igor, I'll have to track that down, but I know that is certainly something that we can generate, again, knowing very well where the lunar surface is at any point in time. Let's see. So I think with that, I'm going to go into just this sort of open-ended tutorial, if you don't mind, and try to sort of highlight a little bit of how we might go about tracking down some of our data. I'm going to start with LROC. This is the LROC webpage, lroc.sese.asu.edu. And once you're there, if you go to the archive, you'll have multiple opportunities, multiple ways to interact with the data. They produce this LunaServe Explorer of basically a dynamic environment to display mapped products. Quick Map, which I've highlighted before, is an awesome way to interact with multiple lunar data sets, not just LRO. And this particular tool here, the data product search tool, is one that I use quite a bit. It is a handy way to search various derived products from the LROC teams. You can do a predefined search for global products, polar products, regional product shapefile, and topographic products. So I'm going to search for topographic products, and just for off the top of my head, we're going to look for topographic product for Tycho crater. So if I type in Tycho and topographic product, probably should have tested this ahead of time. No entries found. Well, that I know is actually a failure on my part, because if I go to Quick Map, and I'm doing that here in real time, you can indeed look at the entire moon, and I'm going to change projections here. And if I do an overlay of narrow angle camera and DTMs, again, these are the produced DTMs that the camera team that LROC has generated. We can see that there is indeed a topographic model for an area north of Tycho crater. That's actually the Surveyor 7 landing site. But I also, if I overlay the stereo observations, so these are observations that were made that can lead to a DTM being produced, you can see that indeed we've covered quite a bit of the interior of Tycho with these stereo observations, but haven't produced a DTM for them. You might ask, why haven't we produced the DTM? As has been explained, the socket set approach is incredibly accurate, but also very time intensive. So these are done at a best effort basis, but you can see that we have a number of stereo observations for Tycho crater. If I go back to the RDR product selection approach, and let's just type in Apollo 16. And again, I'm looking for topographic products here for Apollo 16. I've got to spell Apollo correctly. It's always a good place to start. You can see that for Apollo 16, there are a number of DTMs that have been produced for this particular location. Now you might say, well, why would I be interested in Apollo 16? Again, that is the type locality for exploration for Highlands terrain. It becomes a great point of comparison for remote observation that we have ground truth for. We've driven rovers on, we have measurements of surface properties there that we can potentially apply to other locations across the moon. And you can see that this DTM is actually quite large. It covers not just the place, the strip between North and South Ray craters that they explore, but quite a good portion of the Cayley Plains and the Descartes Highlands. This is available at multiple resolutions. And there are orthophoto mosaics that go along with this at the 50 centimeter per pixel and 2 meter per pixel scales. Let me transition now to talking a little bit about LOLA data. This is the LOLA node, data node, imbrium.mit.edu. And one of the benefits, one of the things I really like about this website is that there are, again, multiple ways to get at the data. But if you wanted a particular topographic product, you would go to the LOLA GDR, that stands for Gridded Data Record. And I'm going to switch over to that tab. You can see how I have tab insanity here. And for a particular, either if you want to look at the South Pole, there are multiple resolutions for South Polar DEMs. Again, sort of nested within each other, starting from 45 degrees and poleward, all the way down to these super high resolution products, 87.5 degrees and poleward at 5 meters per pixel. In addition to having information about the DEMs, there's also these count maps that tell you how many measurements at a specific location were collected that go into production of that DEM. It's a certain sense of, again, how much data density we have for any particular location within these regions. I mentioned earlier that there is these higher resolution DEMs that the LOLA team has produced. Let me pull that link up here so you can at least see what that looks like in quasi real time. And again, these are incredibly useful products for some of these, again, producing high derived products, slope, visibility, things like that. So along with the topographic product, there are count maps, as well as some of these derived products as well. And they produce this very handy method for identifying where we have those 5 meter per pixel DEMs. Okay, so let's see, I've got about 5 minutes left. Let me check into the Q&A for a minute. Can we sort out or screen out the DTM search by meters per pixel? Well, so for LROC, their topographic products are all going to be essentially in that 2 to 5 meter per pixel range, depending on the quality, the resolution of the image that was used to make the DTMs. But for LROC, they're all going to be within that 2 to 5 meter per pixel range. Let's see. I think for the rest of these, I'm going to get into answering those after my presentation. But Angela, if it's all right with you, I'll cede my time here for more discussion or questions.
Yeah, thanks, Noah. That was great. Thanks for showing that off. I'm very impressed in your live demo ability.
It's terrifying. Never do that again.
I always pre-record demos. I think, I mean, we have a few questions in the in here, but I think, like you said, they probably mostly can be answered via typing. I think, I mean, I don't have any particular questions. I guess this was really nice. It was a nice review to show off kind of where the things are.
I have a quick one for Noah, if you don't mind.
Hey, Carolina. No.
Hey, so do you think it would be possible to point people to maybe the super high resolution data sets that have different types of terrain? So a high resolution example of like a very rocky area versus a not rocky area, that kind of stuff, just so that people can maybe see the difference. I don't know the right language or, you know, categories of terrain, but if you could touch on some of that, I think that might be helpful.
What a great question. And in my last 3 minutes, Angela, if it's all right, I'd like to just run with that. So am I still sharing my screen, by the way? I don't really know.
You are.
I am.
Yes.
It says I am screen sharing. So let me show you how I would tackle that. It's a really clever question, Carolina. Thank you. One of the other products from an LRO instrument is a rock abundance map by Diviner. Diviner is a thermal camera thermal infrared camera that measures temperature of the surface of the moon. And from that, we can estimate rocks at the surface. And so let me bring that map up. This is sort of the real-time joy of being able to work with lunar data. So rock abundance, and again, I sound like a broken record. That's okay. We know how the moon works. We know that there are not, in general, rocks scattered across the moon randomly. If there's a large, fresh impact crater, that's going to be the source of blocks. And so we can use the images to infer where we might expect to see rocks. What you see here is a map. Areas in blue are estimated to have essentially no rocks at the surface. It doesn't mean there are none, but not in a concentration to change the thermal properties of the surface of the moon. So you can see interior of Tycho, very rocky. That jives with our understanding of how rocks work at the surface of the moon. Let's see, I don't want to go too crazy about searching and hunting, but let me talk about at least one area that I know we have that is abundant in rocks and we have a DTM for. And again, that's a good point, is that we have DTMs for mare surfaces, we have DTMs for highland surfaces. Depending on where you're going or what you're trying to understand, you want to go to the appropriate like terrain. Don't use a highland surface to understand the mare. Don't use a mare surface to understand the highlands. But for instance, let's see, where am I here? Let's talk a bit about, again, one of these places that we know, or we think we know relatively well. And so I'm going to zoom in on the Apollo 17 landing site. Why? Well, one, we know we've collected a number of stereo observations. We have, again, these high resolution topographic products. And indeed, a small portion of that landing site is, according to the Diviner data set, rocky. And so as I zoom in on the landing site, you'll see that there's this small central region right here that really pops out in the rock abundance map. And we indeed landed just to the north of this small area called the central cluster. And as I zoom in gradually, I'm going to turn off the rock abundance map. I hope that you all can see the color there. Again, the joy of this data set is as we get closer and closer, you'll start seeing in this area all these little rocks popping out in the surface. You can see boulders there, boulders there. This is Steno Crater. This is where the first EVA of Apollo 17 went to. They actually explored an area just to the north of here, but you can see all these little blocks scattered at the surface. What a rich geologic wonderland. Now, if I put on top of this, and I've got to stop moving around. If I put on top of this, for instance, that DTM, and then I promise I'll wrap up here in a minute, Angela. I'm sorry, I'm going long. If I put on a shaded relief map of that, for instance, here, as that topographic product pops up, you can start seeing where some of these small boulders indeed start showing up. Again, this is at 2 meters per pixel. You can see that boulder there, boom, pops up in the DTM. And indeed, if I zoom out, and Angela, if I just take a little bit of prerogative here, if we zoom to the north and actually head up to the actual landing site, I can prove myself right or wrong by actually showing where the lunar module is in the topographic data. So again, in this case, where we have large boulders, boom, they pop out in the topography. I don't want to sound like Emerald with all these booms, but it becomes so clear, and you see it not only in the image, but in the topographic data. Again, one could go down a rabbit hole over hours and hours and days, as some of us have done, just hopscotching around the moon, again, at this scale, which is just such a joy. I'll use the overlays to help point ourselves in the right direction here. So if we zoom up to the north here, here's where the lunar module and all of the experiments were deployed. And again, as we zoom in, I'll take that nomenclature off so you can see there's the shadow of the LEM in the image. And please don't prove me to be a liar. Lay on top of the topography, and you can barely see that little bump right there. That's the lunar module sitting up on the surface almost 50 years after it landed. And indeed, some of the larger rocks that were explored pop up in the topography as well. So again, hazards, they become very clear. Some of these features are readily apparent even in the 2 meter per pixel range. And that's my story, and I'll stick to it.
Thanks, Noah. That was really good. I was actually going to ask you to like show some images and kind of do that. So that worked out perfectly.
I pleased aim.
We know a lot about what the moon looks like and a lot about how it works from all of the great science work that folks do. So these are all really good things to show. So thank you very much. Yeah, I guess there's some other questions in the Q&A tool, and we can look at those.
I'll take those offline, but I did also, Madeline wanted me to be clear, and is that the South Polar products, those 3 that I showed, were work produced by DLR, our colleagues at DLR, and LROC is hosted and shared. But certainly, it's a global effort to get these data out to the world.
All right.